some models and simulation method that especially used to describe some properties that we just mentioned in our first class. Okay, the first one is CH3.Crystal growth, and the second one is the dopant that incorporated our CZ method, and also the zone refining MZ growth, and we will talk about some point defects or rigid the oxygen and the carbon in your silicon. Okay. So how can we model the CZ method? So the first thing is we introduce the continuity equation of heat flow. Okay, and those heat flow, because how can we quantify the growth method? The first important thing is we need to determine the pooling rate, right? Like at certain diameters that we want to grow the material, we need to determine the pooling rate. Okay, so that's the goal of this model. We try to use some physics and mathematics to model the CZ growth method, and hopefully we can get a growth rate. Okay. Now, the continuity equation of heat flow describes the heat flow rate into the volume must equal to the heat flow rate out. Okay, so in equals to out. Okay, that's the continuity means. Okay, so the flow rate can use the area times your velocity to describe your flow rate. Okay, and we use rho as the heat flow and J is the heat flux. And but in the physical terms, in the physical world, there's a divergence of the three-dimensional vector field. But here we can just describe this into one dimension. Like for example, we will use like x direction only. But remember, it's basically it's a three-dimensional divergence. Okay. Okay. The heat. Okay. Let's see these figures. Okay, for example, here is a solid silicon, and this is a liquid silicon. Right. So here we have a higher temperature. Here. So the heat will flow from right to the left. Okay. And if you consider that here we pull this ingot out of the melted polysilicon, and there's an interface between solid and liquid, and that has to satisfy energy conservation, which means the heat flow during this solidification that's obeying this continuity equation like this. Okay, and then that's the basic continuity equation that we can understand. Very similar to what we have learned in the semiconductor physics. We learn like continuity equation, we learn like drift diffusion equations. It's very similar to that. Okay, and here just the schematic pictures that we have liquid silicon here, and this is solid silicon, and we have isothermal distance. Okay, the x isothermal line and isothermal line X2. Okay, and our goal is to try to find a relationship between pool rate and crystal diameters. So that and this freezing happens between isothermals X1 and X2, between here, begin to freeze. And we will begin from our heat balance. Okay. So write down the heat balance in terms of words. Okay. There's a latent heat of crystallization plus the heat conducted from melt to crystal, or equals to heat conducted away. Okay. More frequently as well. You can check from here. Basically, heat flow out of the liquid equals to the heat transfer to the solid. So we can write these three terms here. The first one is the latent heat. So we have a latent heat of fusion is a constant, and dm dt equals to the amount of freezing per unit time. Okay. And the second term on the left-hand side of this equation is equals to the heat conducted from melt to crystal. So this is we use the thermal conductivity of liquid, KL here, and we have dt dx1 along this isothermal line, and we have area equals to A1. Okay, so that's the heat flow out of the liquid. It will either conduct it from melt to crystal, or begin to change from liquid to solid, so that will lose heat as well. And on the right hand side of this equation is equal to the heat conducted through your solid phase. So you have a thermal conductivity of the solid, we call it Ks, and also you have the temperature gradient at isothermal line X2 here, and the A2. Okay, I think it's very easy to understand this. Now, we want to know the rate of growth, and we can use the Vp, okay, that's velocity, to describe this growth rate or the pool rate. And N is the density and A is the cross-section area. So the M equals to your volume times your density. Okay, so in the previous equation we have like how many amounts of silicon begin to freeze out and become solid. So this dm dt can be written as volume times density. The density is n, and your volume can you can use your area times x2 to represent your volume. So here this dm dt, so we can take differentiation this dt here, and x2 becomes Vp, right? So because you have dx2 dt, that'll be your pooling rate Vp here. Okay. And in your in these equations, we try to we can neglect this term, okay? because in your liquid side of your silicon, your dt dx basically is very, very small. Okay, so we can neglect this middle term here. So these equations, we have two terms left. So L times dm dt will be smaller or equals to your this term. So let's move those parameters or rearrange these parameters. The equation will look like this. Okay, let's put this dm dt, plug it to here. And then we can move this, if the A is the same, okay, so we can move this NL to the right hand side. So we have our P pulling rate, the maximum pulling rate equals to this. So this is the upper bound of your pull rate. Right? But the heat transfer to your solid, we need to replace this term dt dx2 because the rest of the parameters we already know that. So in order to replace dt dx2, we need to consider the heat transfer process. Okay. So here is the latent heat of crystallization A. They will transfer up to the crystal B, and is lost by radiation C. Okay, so we firstly neglect the heat lost by the seed. Okay, although there's some part of heat will be lost through this seed, but we can consider that most of the heat is lost by the radiation. So the heat radiation from the crystal will follow by the Stefan-Boltzmann law. Okay, that's I believe that's described in your modern physics textbook. Okay, that's the Stefan-Boltzmann law. dq equals to this. It's proportional to your T 10 to the 4. Okay, so now we can do some math. So we have the Q. The heat conduct up the crystal. Okay. This term Ks times dt dx. So this is the area. This is the conductivity of solid silicon. So we can plug this equation 5 into equation 4. Okay, we can differentiate this 5, equation 5. Now we can take partially differentiation of this equation. So we have dt dx differentiate 2 times, and we have dk as with dx here. But this term, we assume that okay, it's almost constant, so we can neglect this term, and then we have this term left. Okay. Now we can plug this equation 6 into equation 4. Okay, you plug this into here. Now it becomes differentiation equations for t. Okay. Now again we do some approximation that your Ks is roughly proportional to inversely proportional to your T. So we can plot this Ks with this Km, which means the thermal conductivity at the melting point. But once you increase, you reduce the temperature, you can increase your conductivity. So we plug this in, and we have this equation 9. So okay, by solving this differential equation, we can get the T at x equals to 0. So we can have dt dx. And this dt dx we can plug into the equation 3 here. So we can have our pulling rate. So okay, we solve this analytically. We have a T, and we can take the differentiation and then plug into equation 3. Then we will have equation 10 here. Okay, so basically you can see here all the parameters are known because like Km or Tm, they are the temperature or the thermal conductivity at the melting temperatures, and you have N and L. The only variable is your R. R is the radius of the wafer that you want to have, right? So it's very intuitively, you can see your V is proportional to your square root of R. 1 over your square root of R. So if you want your R larger, which means you want the radius or diameter larger, you have to reduce your pull rate. Right? You have to pull it slowly. So that's the you can very easy to imagine that. When you want your diameter of your substrate smaller, then you have to pull faster, right? Or become like smaller. So here just use some physical model that we can quantitatively to describe this number. Okay, but okay, so if we put all the numbers in, we can get just a quick estimation of the pulling rate is an hour. You can put 24 centimeters for a 6-inch crystal, but actual values are 2 times less than this, because you have to consider a lot of things. Like during our derivation, let's say we neglect the heat conducted through the seed. We only consider the heat loss through radiation. Okay, so in the real situation, in the real chamber, we will use a lot of sensor to monitor during your growth of ingot. Okay, so we can try to do some in situ monitoring your like, for example, your diameter of your ingot. Okay, so here just another papers that they created a model in the VLSI technology. It's from the Simon's textbook, but originally it's from the VLSI paper. That people do the experiment and try to build out the model. So you can see that the 49 millimeter per minute is the pulling rate. And also here the dashed line is a theoretical growth rate, and do some experiment. This is the average rate that you have to be larger than this one, because if it's lower than this, those solid probably will remelt into liquid. So you have to maintain a certain cooling rate. Okay. So here is we try to use segregation behavior to model the FZ growth method. Okay. Those impurities or dopants, we can add this into the melted silicon to provide N or P doping. Okay, so if you want to grow P-type substrate or P-type ingot, we can put some boron. Or if you want to put grow N-type substrate, we can put other like arsen or phosphorus into your melted silicon. But this dopant incorporation process is complicated because they will segregate, which means they have different concentration in the liquid and in the solid. Okay. And those segregation will occur between the liquid and solid phase of material. Okay, so we can do some experiments to check these segregation coefficients. Okay, here we define the segregation coefficient K0 equals to concentration in the solid divided by the concentration in the liquid. Okay, so both are function of time. Okay. And this is the table for silicon or for gallium arsenide substrate with different dopant here. And you can see the segregation coefficient sometimes is greater than 0, sometimes it's less than, it's greater than 1 or less than 1. If this is larger than 1, means your concentration in solid is larger than the concentration in liquid, which means your defect or your dopant may tend to segregate in solid rather than liquid. And if it's less than 1, that's the other way. They try to segregate in liquid rather than in solid. So for the silicon, you can see that all of them are less than 1, which means that the impurity prefers to stay in the liquid. So that's why we can use the FZ method to purify the silicon. Because once we heat up and melt the silicon, the impurity or the dopant will tend to stay in the liquid side. And once you move the coil, you can just move away all the impurities. Okay. So, but that reminds us that when we talk about the FZ, right? As the crystal continue to pull and move upward, you continue to increase your impurities concentration in your liquid. So once it freeze and turn back to solid, those material will contain more concentration of impurity or dopant. So I think that's 我用中文再说一次好了，就是你在拉这个的时候呢，因为你的 dopant they prefer to stay in the liquid， 所以它跑到 they move to the liquid, but once it solidify or turn back to solid, those solid will contain larger concentration of dopant or impurities. So as your ingot move to the top of your 最上面这个地方 ，OK， 你可以想象 ，you can imagine that the dopant profile or the impurity profile there's more pure material underneath, but as you go upward, the dopant concentration will increase, or the impurity will increase. So that creates a problem, right? You have an ingot and you try to cut it into like different pieces of substrate. If you cut it, if you take the substrate from the bottom of this ingot, it's more pure. But you take the substrate from the top of your ingot, shit, you are not lucky, right? You get a bad one. Right? Can you understand that? So that's the effect of your segregations. Especially you can see that, okay, the order segregation is less than 1. So that will have this problem. Okay? But like for the gallium arsenide, well, some of the dopant, they are just larger than, the coefficient is larger than 1. Okay? Okay, so here, let me ask you a question. Okay. If you want to choose the dopant, right, from this table, which one will you choose? Do you want to choose, let's say, phosphorus, or you want to choose arsen? Like for N-type, which one will you use? Or for the P-type dopant, let's say boron or gallium or aluminum, which one will you choose? Right? So the question back to that, which one will give you more uniform doping profile across your ingot? You want to choose this coefficient close to 1 or much smaller than 1? Which one will give you a more uniform profile across the ingot? Do you know the question? So we want this ingot, the dopant or the impurity profile across the ingot is more uniform. That's the target we want, right? Otherwise, it's like a lottery, right? You take this wafer or take this wafer. The properties are, very different. So we want the dopant that has segregation coefficient close to 1, which means that your concentration in liquid or in solid, they are more close to each other. They are more similar, right? So once when you do those either CZ or FZ, well, you can get a more uniform doping profile. Because remember that your dopant profile is the same as the one you just freeze, melt it and freeze back to the solid, right? So 我们希望这个的两个要越接近的话呢，你在做这个过程当中，它不会落差太大，所以你如果今天两个差很多的话，表示它dopant都全部跑到 liquid 里面去，就大量的集中在 liquid，所以你越到后面的话，你的那个前后的差异就会越大。那如果这两个是越接近的话呢，到后面虽然还是有差异，但是会前后的这个差异会比较小。So in this case, we'll choose boron because it's more close to 1. So that's the most wafer you got is P-type dopant and by boron. Okay, it's doped by boron. Okay, I think it's about time. We will send this to our next lecture. Okay, so just okay. Thank you.